You think you know what light is. That's the assumption. Light is something that moves. It travels. It has a speed. Very fast. The fastest thing we know. You learned the number in school, or at least you heard that there is a number. You don't usually question it. Why would you? Light goes fast. End of story. But that's not an answer. That's just a label. The simple question is this: how fast does light go? And more importantly, how does it know? That sounds like a strange way to put it, but think about it carefully. When a car moves, its speed depends on the engine, on friction, on how hard you press the pedal. When you throw a ball, its speed depends on how strong your arm is, and whether you're standing still or riding on a train. Speeds add. That's how motion works, or at least that's how motion has always worked. So you'd expect light to work the same way. If you're standing still and you turn on a flashlight, the light moves away from you at some speed. Fine. But if you're moving, if you're already going fast, you'd expect the light to move faster still. Light plus you, just like the ball. That expectation feels so obvious that people rarely notice it's an expectation at all. It feels like common sense. And common sense, when it's wrong, is the most dangerous thing of all. This question bothered a lot of people long before Einstein. It bothered them quietly, in the background, because the world seemed to work anyway. But once measurements got precise enough, once people actually tried to measure the speed of light carefully, the discomfort started to show. Galileo was one of the first to seriously ask whether light takes time to travel. Not how fast it goes, just whether it's instantaneous or not. He tried an experiment with lanterns on distant hills. One person uncovers a lantern. The other responds as soon as he sees it, and you measure the delay. The result was inconclusive. The distances were too small. Light was too fast. But the question was now on the table. Later, something strange happened in astronomy. People started tracking the moons of Jupiter very carefully. These moons orbit Jupiter like clockwork. Or at least they should. Newton's laws work beautifully for orbits. If gravity followed a simple rule, you could calculate exactly when a moon should disappear behind Jupiter or emerge from its shadow. But the times didn't always match. Sometimes the moons were early. Sometimes they were late by minutes. That's a huge error in astronomy. Something was wrong. And here's the key part. The error depended on where Earth was in its orbit. When Earth was closer to Jupiter, the moon seemed early. When Earth was farther away, they seemed late. Ole Rømer noticed this and said something very bold. Maybe the moons are doing exactly what they should. Maybe the delay is in the light itself. Maybe it takes time for the light to travel from Jupiter to Earth, and that time changes as the distance changes. This wasn't philosophy. It was a calculation. And when he did the math, the numbers lined up. The speed of light came out finite, enormous, but not infinite. That alone was already strange. Light wasn't instant. It moved. It had a speed. Once you know that, once you accept that light moves at a finite speed, the next step seems obvious. Measure it. Measure it carefully. And people did. Over and over, better mirrors, better clocks, longer baselines. The number settled down, but then something happened that nobody expected. No matter how you measured it, the speed of light came out the same. At first, this didn't seem shocking. Of course it came out the same. Why wouldn't it? But that's because people were unconsciously assuming something else in the background. They were assuming that the speed was being measured from the same state of motion each time. The real test came when people started asking a more careful question. What if the observer is moving? Here's where it gets uncomfortable. Imagine you're standing on the ground. You shine a flashlight forward. You measure the speed of the light. Fine. Now imagine you're on a train moving forward. You shine the same flashlight in the same direction. What should happen? If you've ever thrown a ball from a moving train, you already know the answer. Your intuition gives you. The ball goes faster relative to the ground than it would if you were standing still. The train adds its speed to the ball. That's how velocities combine. That's how the universe works. So light should do the same. Light from the moving train should go faster than light from the stationary ground. Light speed plus train speed, except it doesn't. No matter how fast the train goes, when you measure the speed of the light, you get the same number. Always, not approximately. Exactly. This wasn't a one-off mistake. It wasn't a bad experiment. People tried to find ways around it. They assumed there must be a medium carrying the light, like air carries sound. They called it the ether, a universal background substance that defined absolute rest. If that ether existed, then light would have a speed relative to it, and observers moving through the ether would measure different speeds depending on their motion. That would restore common sense. So people tried to detect Earth's motion through the ether. They built exquisitely sensitive experiments. They compared light beams moving in different directions. They rotated the apparatus. They waited for seasonal changes as Earth orbited the sun. Nothing. No matter what they did, the speed of light refused to change. This is the point where most explanations go wrong. They say Einstein postulated that the speed of light is constant. That makes it sound arbitrary, like a rule pulled out of thin air, like an axiom chosen for elegance. That's not what happened. Einstein didn't start by declaring the speed of light constant. He started by refusing to ignore a fact, a stubborn, annoying, experimentally verified fact. Light doesn't care how fast you're moving. That should bother you. It should bother you deeply, because it means something else you believe must be wrong. You can't just say, well, that's how light behaves. That's not an answer. That's a dodge. The real question is, how can this be possible at all? If speeds add, light shouldn't behave this way. If light behaves this way, speeds don't add the way you think they do. Something has to give. This is the simple question about light that broke physics. Not how fast is it, but fast compared to what? Compared to you, compared to the train, compared to the Earth, compared to what exactly? In everyday life, you don't think twice about this. Motion is relative. If you're sitting still, the world moves past you. If you're moving, the world looks different, but time stays time. Length stays length. Everyone agrees on those, or so you think. Einstein looked at this mess and did something very dangerous. He took the experiment seriously, more seriously than common sense. He said, suppose the speed of light really is the same for everyone. Not approximately. Not because of experimental error, but exactly. Then ask what must be true about the universe for that to be possible. That's the key move. Not inventing a rule, but asking what kind of world would make the rule unavoidable. Think about this carefully. If two observers are moving relative to each other, and both measure the same light beam, and both get the same speed, then something else must differ between them. They can't both be using the same rulers and the same clocks in the same way. Either distances change, or time changes, or both. There is no other option. This is where most people stop following. Because up until now, the story has been about light. From this point on, it's about you, your clocks, your rulers, your sense of now. And this is exactly why Feynman loved this topic, because it shows how a small, innocent-looking question can force you to abandon ideas you didn't, even though you were assuming. Light didn't break physics by being mysterious, it broke physics by being consistent. Relentlessly consistent. In the next segment, we'll see what happens when you accept that consistency and follow it all the way through without flinching. At this point, you have a choice. You can give up on the experiments, or you can give up on intuition. Physics chose intuition. Suppose two people are moving relative to each other. One is standing still on the ground. The other is riding a train. They both shine a flashlight forward. They both measure the speed of the light. And they both get the same number. This is not a trick. It's not an illusion. It's not because the instruments are flawed. It's because the universe insists on it. So ask the only question that matters now. What must be different between the two observers? The answer is not light. Light is doing the same thing in both cases. The answer must be space and time. That sounds abstract, so let's slow down. Speed is distance divided by time. That's all it is. If two people measure the same speed but they're moving differently, then either they're measuring different distances or they're measuring different times or both. There is no third option. Before Einstein, nobody seriously questioned time. Time was universal. A second was a second everywhere for everyone. Clocks might be inaccurate, but time itself was absolute. Space, too, was assumed to be fixed. Rulers might bend, but length itself was supposed to be the same for everyone. Einstein said no. Not tentatively, not metaphorically. Literally no. If the speed of light is the same for everyone, then time itself must flow differently for different observers. That sentence alone should stop you. Time flowing differently is not poetic language. It's not psychological time. It's not about perception. It's about clocks, physical clocks, atomic clocks, mechanical clocks, any clock you build. They do not all agree. Imagine a clock on the train and a clock on the ground. Each one ticks normally for the person next to it. Nothing feels strange locally. But when you compare them, when motion enters the picture, they disagree. The moving clock runs slower. This isn't because it's broken. It's because time itself is behaving differently along different paths through the universe. Here's the uncomfortable part. This isn't something Einstein added to make the math work. This is something the universe demands to keep light consistent. Think about a simple thought experiment. A beam of light bouncing between two mirrors, one on the floor and one on the ceiling of a moving train. To someone on the train, the light goes straight up and down. To someone standing outside, watching the train pass by, the light traces a zigzag path, a longer path. Same light, same speed. If the path is longer for the outside observer, but the speed is the same, then the time must be longer. The clock on the train must be ticking more slowly. That's not interpretation. That's arithmetic. People often ask, but who is really moving? That's the wrong question. Motion is relative. Each observer is allowed to say they're at rest. The laws of physics don't privilege one over the other. So the universe does something extraordinary. It allows time itself to become relative. Length has to change too. If time changes but length doesn't, you still can't keep the speed of light fixed in all directions. So lengths contract along the direction of motion. Rulers shrink, not because they're squeezed, not because of stress, but because space itself is arranged differently depending on how you move through it. Again, nothing feels strange locally. Your ruler still works. Your clock still ticks. But when compared across motion, they disagree. This is where people start to resist. They say that can't be real. It must be an illusion, a trick of measurement. So physicists tested it. They took precise clocks, put some on airplanes, flew them around the world, and compared them to clocks left on the ground. They disagreed, exactly by the amount predicted. They took unstable particles that decay in a known time. When those particles move close to the speed of light, they live longer. Not subjectively, measurably. You can count how many survive. You can predict it. And the predictions work. This is not philosophy. It's not interpretation. It's bookkeeping. Now here's where the original question about light comes back with force. If time slows down as you move faster and lengths shrink, what happens as you approach the speed of light itself? The answer is not subtle. Time dilation grows without bound. Length contraction becomes extreme. To reach the speed of light, time for you would have to stop entirely. Your clock would have to freeze. And to make that happen, the energy required grows without limit. This is not because of engineering constraints. It's not because engines aren't powerful enough. It's because the structure of space-time itself refuses to allow it. The closer you get to the speed of light, the harder it becomes to go faster. Not gradually, relentlessly. Feynman liked to emphasize this point because people often misunderstand it. They imagine the speed of light as a barrier, like a wall you crash into. That's the wrong picture. There is no wall. There is no moment where something dramatic happens at the speed of light. Instead, the universe is arranged so that you can get arbitrarily close, but never quite there. It's like trying to reach the edge of a circle that keeps stretching as you move. Why does this happen? Because the speed of light is not just the speed of light. This is where the original question breaks completely. We asked, why can't anything go faster than light? That assumes light is special and everything else is limited by it. That's backwards. Light is not special because it's fast. It's fast because it's special. Light has no mass, zero, and because it has no mass, it cannot be at rest. It must move at the maximum possible speed through space-time, not a chosen speed. The speed of light is not a property of light. It's a property of space-time. This is the reframing that changes everything. Space-time has a built-in conversion factor between space and time, a maximum rate at which cause and effect can propagate. That rate is what we call the speed of light. If light didn't exist, that rate would still be there. Think about that. The universe has a maximum speed, not because light happens to move fast, but because the universe itself has a geometry that doesn't allow information to move any faster. Light simply reveals it. This is why Feynman insisted on stripping away the mysticism. There is no cosmic traffic law saying nothing may exceed this speed. There is only structure, and once you understand the structure, faster than light motion doesn't just seem difficult. It stops making sense. To go faster than light would require rearranging cause and effect. It would require effects to happen before causes in some frames of reference. It would require time to run backward for some observers. That's not forbidden by taste. It's forbidden by consistency. And consistency is what started this whole story. In the final segment, we'll see how this simple question about light reshapes not just motion and time, but the very idea of what now means, and why the universe had no choice but to be this strange. By now, the original question about light has completely disappeared. It started as a question about speed, about how fast something moves, but it quietly turned into a question about structure, about how the universe is put together. And once you reach this point, there's no going back to the old way of thinking. Because the strangest consequence of all isn't time slowing down or rulers shrinking. It's what happens to the idea of now. You think there is a present moment, a universal present, a single slice of time that everyone shares. You assume that what is happening right now for you is also happening right now everywhere else in the universe. That assumption feels harmless, obvious even, but it cannot survive the speed of light. Imagine two events happening far apart in space. One on Earth, one on a distant star. Are they happening at the same time? For Einstein, that question had an answer. Of course they are, or of course they aren't. Time was universal. You just had to synchronize clocks. But synchronization itself depends on light. You synchronize clocks by sending signals, light signals. And because light takes time to travel, and because its speed is fixed, different, observers disagree about which distant events are simultaneous. This is not a technical detail. This is the collapse of the idea of absolute simultaneity. Two observers moving relative to each other will slice space-time into now in different ways. What is present for one can be future or past for another. Nothing physical happens at that boundary. No explosion, no shimmer, just disagreement. Feynman liked to point out how deeply unsettling this is. Not because it's weird, but because it's unavoidable. There is no experiment you can perform to find the true present. There is no hidden clock ticking behind the scenes. There is only your frame of motion and mind, and the rules that connect them. The universe does not come with a master timeline. Instead, it comes with a structure that limits how events can influence each other. Light cones, regions of possible cause and effect. What you can affect, what can affect you, and what is forever out of reach. Once you see this, faster than light motion stops being an engineering problem and becomes a logical one. If you could send a signal faster than light, you could send a signal into your own past, not in some science fiction sense, but directly as a consequence of how different observers order events in time. Cause and effect would no longer be consistent. You could receive a message before it was sent. You could create loops where an effect prevents its own cause. The universe does not permit this, not because it dislikes paradoxes, but because its structure doesn't allow them to form in the first place. This brings us back to the deepest misunderstanding about light. People say the speed of light is the speed limit of the universe. That sounds like a rule imposed from the outside, like a governor on an engine. That's not what it is. The speed of light is the speed at which space-time converts time into space. It's the scale factor that tells you how much space corresponds to a given amount of time. Change that number, and you change the geometry of reality. In everyday units, we treat meters and seconds as separate things, but the universe doesn't. Space-time treats them as aspects of the same entity, and the speed of light is the number that ties them together. This is why it appears everywhere, not just in optics, but in electromagnetism, in relativity, in the equations that describe fields and particles. It's not a feature of light. It's a feature of everything. Feynman emphasized this because it removes the temptation to ask the wrong why. Why is the speed of light what it is? That question assumes there must be a deeper mechanical reason. Sometimes there isn't. Sometimes a constant is fundamental because it defines the stage on which everything else happens. Asking why the speed of light is the speed it is like asking why space has 3 dimensions or why time has 1. You can imagine other possibilities. But once you accept this universe, those numbers are part of its identity. What you can ask, and what physics does ask, is what follows from that structure. And what follows is extraordinary. Mass-energy equivalence. The fact that mass itself is a form energy with a conversion factor given by the speed of light squared. That's not a coincidence. It's geometry. The fact that gravity can be understood as curvature of space-time, where light itself follows bent paths. Again, not an add-on, a consequence. The fact that particles with no mass must move at the speed of light, and that particles with mass can never reach it. Not a rule, a necessity. This entire cascade of ideas came from refusing to ignore a simple experimental fact. Light always moves at the same speed. That's the avalanche Feynman loved to describe. One insight unlocking another, not by decoration, not by speculation, but by insisting that the universe makes sense on its own terms. And notice something important. At no point did this story rely on comfort. Nothing here aligns with how the world feels. Nothing here preserves common sense. That's not a failure of physics. It's a failure of intuition. Your intuition evolved to throw rocks, not to measure space-time. It works beautifully at human scales, and it lies to you outside them. The lesson of the speed of light is not that reality is weird. It's that reality is precise. It does exactly what it must do to remain consistent. Light didn't break physics by being mysterious. It broke physics by being honest. Honest about speed. Honest about time. Honest about what can influence what. And once you accept that honesty, once you stop trying to force the universe to match your expectations, something remarkable happens. The pieces fit. The universe becomes strange, yes, but not arbitrary, not chaotic, not magical, structured. And that in the end is the real gift of that simple question about light. It didn't just tell us how fast something moves. It showed us how reality holds itself together.